Guy McPherson here with an informed tech dude, and today we're going to continue our conversation that we began a couple of sessions ago. And with that, Neil, I'd like to turn it over to you, and I'm going to start the slideshow, and you can tell me when to advance the slides.
Guy, thanks. Yeah, I think we continue going backwards in time. Our previous discussions were focused on data going back as far as 66 million to even 400 or 500 million from the fossil record of CO2 and temperature, Earth's temperature. But 400 million years is going to seem like just a couple of minutes in what we're going to do today, because we're going to go back and look at the complete history of life on Earth and the planet from the beginning to sort of get an idea of where life began and how it progressed based on what science has discovered. Hundreds or thousands of scientists over the last 200, 300 years looking at the evidence. And so this first chart is kind of interesting. It's out there. I think it's pretty easy to find. You can find it on Amazon. It's from Encyclopedia Britannica. You can get this as a wall chart. I'm going to draw your attention, if you can put the arrow in the upper left, at this word Hadean. And there's just a bunch of scratched lines. And if you, this is the earliest period, 4.5 million years is how old we think the planet is. And it was hit in its first 500 million years by comets and asteroids, and in fact a whole other planet hit the Earth and blasted the Earth into in a third, and half of that went out and became the moon. So this was a very inhospitable, wasn't even anything you would call an environment. And if you remember from mythology class in the 4th grade, Hades, it's called Hadean because Hades is the Greek hell. And from what I understand, the next period, Archean and Protozoic, from 4 million up to 500 million, 600 million, those first two periods there in the center of the upper band of this chart is where the very first things that scientists refer to as living creatures, they're single cellular bacteria. They may not even really have something we call a cell. The first first forms of algae, single-celled living things. This is mostly in the oceans. This is recovered from very ancient sediments from our oceans. Sponges, jellyfish. Am I correct?
Yes, and this is an important point. Life on this planet emerged from the ocean. It evolved first in the ocean. And so as we treat the ocean, that's how life is going to go into the future.
Exactly. And some of you may have seen a fossil. There were so many of them during the Cambrian period. If we put the arrow at the Cambrian, for not very much money, for I think $1.50. In the Southwest, you can buy a trilobite fossil, which is from the Cambrian explosion. Where, Guy, could you talk about what happened between, in this your profession has named the Cambrian period?
Well, it was a period of the evolution of a huge amount of life, again, beginning with marine organisms in the ocean. And a wonderful book called A Wonderful Life, written by Stephen Jay Gould, describes the unlikeliness of such an event happening. And that event, the Cambrian evolutionary event, caused a great speciation. Great number of species suddenly came into being for the first time. In fact, we can trace our ancestors back to the Cambrian. So were it not for the Cambrian explosion, as it's called, because of the explosion of life that occurred, then we wouldn't be here today. Stephen Jay Gould makes a wonderful point and draws the parallel with the film starring Jimmy Stewart, It's a Wonderful Life, in the unlikelihood of these events happening at any time, much less when they did, and therefore leading to our original precursors, the precursors to mammalian life, and therefore to humans on the planet. That all happened during the Cambrian explosion.
You know, that's a very interesting perspective, and I wish I'd seen it. I have heard of Stephen Jay Gould, but what it reminds me is we tend to think if we know anything about the history of evolution, and we focus recently on the great apes and Louis Leakey and the earliest Australopithecus and various other very recent ancestors of humans, we think of that as the most important thing. But that is just one actually very recent thread, it's dawning on me. And it's no less important. In fact, this Cambrian explosion was the predicate for all the species that we now have. Is that fair to say? Including us.
Yes, absolutely.
So in this chart, we're only at the Cambrian, and we're going to proceed at lightning pace here. As I say, in the US Southwest, you can go into fossil shops and buy for not a lot of money. There are so many of them. There's more rare fossils that you can obtain. But trilobites, everybody has a trilobite. You can get an ashtray with a trilobite at the bottom of it. Uh, so, you know, it then goes through these names, wonderful names: Ordovician, Silurian, Devonian, Carboniferous, Permian. You know, in a Carboniferous, in a future episode, and maybe the next episode, we're going to talk about why the Carboniferous is interesting. I won't give it away right now. But Permian, Triassic, Jurassic, the age of dinosaurs that we embrace when we're kids. We think dinosaurs are cool. That is at the earliest end of the Permian, but mainly, right? Am I right, Guy? Triassic, Jurassic period.
Oh, yes. Yes, absolutely. In fact, the first trees that we'd recognize as trees came about in the Carboniferous. And the original conifers that we call things like firs and hemlocks, that sort of thing, came about during the Permian Triassic period, right there at the boundary between them. And so
Right.
this is, you know, you can go back a long way and find something that we recognize, but you can only go back a little ways to find something that is us, and
Mm.
that everybody would say, oh yes, that's a human. We recognize the coniferous trees, we recognize the different kinds of mammals and so on, but to get to an upright ape, uh, something walking around on 2 feet, that comes much, much later, but is dependent upon all these previous events and organisms as well.
You know, another thing before we progress to the next slides, which really have to help us with time, but it dawns on me that, you know, the story of life on this planet is the story of both the proliferation of families, genus, and species of life, and also their ending, because clearly 9/10 of the species represented here, I mean, the class of fishes, we still have fishes, obviously, but most of the species here don't exist anymore because they went extinct. So this story of life on the planet is a story of explosions of new families, new species, new life, but also the story of the loss of those. They end. We're going to be talking about that.
Yes, in fact, one of Carl Sagan's great lines is, quote, by far most of the species of life that have ever existed are now extinct. Extinction is the rule, survival is the exception, end quote.
Right. So look, before we to progress to the next chart, I note that this wall chart from Encyclopedia Britannica, and you can buy it on Amazon as a poster. I'm advertising for Encyclopedia Britannica, contains these vertical black lines, which actually right there between Cenozoic and Mesozoic, and the vertical black lines are a change of scale of years. You're looking first at tens of millions and then at hundreds of millions. So let's go to really understand the time frame involved in all of this. This chart looks like life arose in 90% of Earth's history, because up there at the Archeon we see the first forms of life emerging. So you might think that the story of planet Earth is the story of life, but let's go to the next slide. So this slide takes all the same information and periods of the previous slide, but puts it in a pie chart, as if all of time, since we know from scientific evidence that the Earth began as a planet, was one pie. It begins with this Hadean period, which is, a very large slice, the Archean period in red, and the Proterozoic period in green. That takes up 7/8 of the pizza pie. It's in this last slice of an 8-slice pizza pie that we get the Cambrian explosion, Ordovician, Silurian, leading up to the Holocene, which is the most recent period, technically the period that we're currently in, and the last 200,000 years of which is relevant directly to the speciation of humans. This gives a whole different view of geologic time, and how we should think of how much time it took life to emerge from even a single fungal cell or string to a complex life form.
And you'll notice in this graph, they have rounded to the nearest 0.1%. The Holocene accounts for 0 time. That's how small it is.
Yeah.
That's the only world we've ever known. And
it's not even a full tenth of a percent. Yeah.
Right.
Let's go to the next one, which is, again, similar information, but I hope it helps here. This is harder to read, but what you read this clockwise from the bold formation of the Earth at 12 o'clock position. The Hadean takes us till 2 p.m. The Archeon takes us to 5:30. Then if this were one day, and the atmosphere only gets oxygen in the early stage of the Proterozoic. By 10:30, we're into the Proterozoic and the first forms of what we really would identify. Scientists could even strain their definition to call life, begins there. And again, it's in the last hour, an hour and a half maximum, that what we view as life that you can see the remnants of in the museums of natural history of our world is all from the last hour of the day, hour and a half of the day. Is that fair to say? That's how I read it.
Yes, absolutely. You can see the Cambrian explosion again, and the first vertebrate land mammals arising shortly after, and that's all very recent.
Yeah.
So, we've taken up a huge slice, several slices out of this particular pizza before we finally get around to the fact that there's the first vertebrate land animals are immediate precursors.
If someone were to react, well, if things went extinct, they could just evolve again, the appropriate response would be, well, yes, maybe in 3 million years. Yes, maybe. One doesn't know.
Yes, or more likely
3 billion years.
Yes, that's what I was going to say. More likely 3 billion years.
Yeah.
That's a long time. If you're going to wait it out in your bunker, it's going to seem like a really long time.
If you're going to be there with your fishing line saying, I'm going to wait, I got to wait till the fishing is good again, that'll be 3.5 billion years. What are you going to eat in the meantime?
Night crawlers, apparently.
Let's go to the next. Actually, before we go to the next slide, I'm reminded that you have defined on a number of occasions your particular scientific field of conservation biology, and as I recall, it's got at least 2 or 3 or 4. If you give the briefest definition, it has to do with this growth of life and species. Can you redefine again, since my memory is not very good, what the field of conservation biology that you have worked so hard in is mainly about?
Yes, conservation biology is underlain by 3 pillars. or three primary ideas that contribute to the whole discipline. And it's difficult to even call it a discipline or a field because it overlaps with so many others. But there is speciation, the first time a species comes into existence through evolution, such as we've already talked about with the Cambrian explosion, and that is evident here with first dinosaurs, first vertebrate land animals, first hominids, leading to us. Okay, so that's speciation. Then there's extinction, of course, when the last individual of a species dies. And then importantly, underlaying the speciation and the continued existence of any species is habitat. So those are the three big factors: speciation, the existence of habitat and the retention of habitat, and then extinction. And the extinction begins with extirpation, which is the death or removal of populations of a species. So as long as there's a population here and there, as long as there's one population left, we're not calling the species extinct yet. It's only after all the populations die that we call it an extinction event. And here we are in the most profound extinction event in planetary history.
So I'm really glad you defined it, because people often don't realize that the study of extinction is as important and part of biology and conservation biology as the study of habitat, speciation, what makes a species successful, what aspect. Am I right? All of this would include the questions such as how does a species fit into a habitat? What parts of the habitat that it relies on are most critical for that species? Some parts of the habitat could change and it might not affect that species, might affect another species that is food for that species. Am I right? I'm just
Yes.
scratching the surface of all the things that go into habitat.
Yes,
Right?
absolutely. The critical, I mean, it's important to recognize that habitat involves a whole bunch of different things. The ability to find food, the ability to find water, if you rely upon water for your existence, as we do. Habitat is comprised of things like temperature, can't get too hot, can't get too cold. That's why the Hadrian period was named what it was named, was because it was too hot for essentially any life form on this planet. And so we have to keep in mind when a species comes into existence and whether habitat exists for it. A species might come into existence and there's no habitat for it, so that first individual is disappears immediately. That might have happened, for all we know, millions of times throughout planetary history, that a species came into being and there was no room for it because there was no habitat for it.
So it lasted only a short time. It developed a difference that seemed to work for a while, but then became maladaptive, or the habitat changed and it couldn't adapt. Is that fair
Right.
to say?
Yes, and you have to remember that these genetic changes are random.
Mm.
So as a result of random variation, a species might or might not fit. So for all we know, there are dozens of species that come into being one time or less than one generation for every species that comes along and persists for many generations.
For
We,
long enough, for long enough to leave a fossil record for us, even a
yes,
find. Yes.
absolutely.
This explains also why people may react that every once in a while a news item is a new species was discovered, either a fossil species or a new existing species, and people might think, well, that means that things are not going extinct. Can you
Right.
speak to that?
It's all
If
fine.
it's all fine, if we're still discovering new species, then how could extinction be a problem? I think in the next few slides we're going to answer that. So I included this slide, Guy, and I want you to speak to it because it refers to, this is like the first of several slides that go into a lot more detail, but this one has a phrase that I don't think I've ever heard: background extinction rate. That there are these mass extinctions that we have lots of evidence, but there's also a thing called the background extinction rate. Can you speak to that?
Oh, yes. And this is something that most people do not understand. There currently are millions of species on the planet, but some of them are going extinct. And because of our actions, more than 200 species are going extinct every day. But there's this background extinction rate at which the speciation is almost perfectly matched to the rate of extinction. If it weren't, then we would have a planet so full of different species that we'd have a hard time finding a place for us. Extinction is always happening at some relatively low background level. Speciation is always happening, and speciation has been happening throughout the human existence until the last several years. Speciation has been happening at about the same rate as extinction. In fact, a little bit more, a little bit faster. Species are coming into existence a little bit faster than they are going extinct until quite recently, of course, when human activities have been driving species to extinction at a far faster rate than they've been evolving into existence.
Just thinks of an accounting principle. If you are making more money each month than you're spending, then your wealth is growing. But if you then go into a period where you're making less money than you're spending much more, then your wealth is shrinking. If on the planet new species are actually coming into existence at a certain rate, and the rate of extinctions is slightly lower than that, then your planet is growing in terms of its diversity of ecosystems and its variety of animal and plant life. And you could make the case that it's more robust against total extinction. But if for a long period, or you set in motion a period where the extinction rate exceeds for long, long periods the new species rate, would I be right that that planet is losing its life?
Yes, absolutely. And we talked about the Cambrian explosion. During the Cambrian, the speciation was vastly outstripping the rate of extinction. So that's why it's called the Cambrian explosion, is all these new species came into existence that we can identify through the fossil record.
Well, look, if before we go further, let's use Encyclopedia Britannica, which occasionally has really good summaries. I think there's a video that might be helpful to people. We hope it is only intended for educational use. We are educators here. So let's see if we can cue that up.
In the 1970s, a scientist named Jack Sepkoski embarked on the most ambitious fossil hunt ever. But instead of digging in the dirt, he dug through dusty piles of academic research and scraped together a record of all the ocean-dwelling creatures known to science. It was tedious work, but the data it yielded gave rise to perhaps the most famous chart in paleontology, a tally of marine life over time that revealed 5 catastrophic global biodiversity crashes in Earth's past. Those crashes, known as the Big Five mass extinctions, are commonly believed to have been the biggest die-offs in Earth's history, both in and out of the oceans. They include that time 66 million years ago when a huge meteorite took out the non-avian dinosaurs, as well as the even more apocalyptic extinction at the end of the Permian period, which wiped out more than 90% of Earth's species. But the Big Five weren't the only big mass extinctions, and they might not have even been the biggest. Take the Great Oxygenation Event of 2.3 billion years ago. Evidence from ancient rocks tells us that levels of atmospheric oxygen spiked around this time, poisoning the oxygen-hating microbes that had dominated Earth for well over 1 billion years. And yet, we can't really say how that extinction compares to the Big Five, because its victims were microscopic and left virtually no signature in the fossil record. In fact, the fossil record only captures a tiny fraction of the life that has ever existed on our planet, but it also captures a different fraction from one period to the next. In general, the record gets less and less complete the further back in time you go, but that trend is complicated by several other factors. For one, we have a lot more fossils from swampy places and periods of the past, not necessarily because those periods were more diverse, but because the calm, muddy conditions were perfect for preservation. We also have a lot more rock from some periods of time than others, and in general, the more rock we have, the more fossils we find, and the more abundant life appears to have been. In other words, the fossil record is inconsistent, So we can't just tally the number of species and take the results at face value, as Sapkowski's Big Five chart did. But paleontologists have used some clever statistics to adjust for those inconsistencies. And the latest diversity curve makes it look like there have been 8 major mass extinctions rather than 5. But you could also count 11, or just narrow the list to the 3 most massive. In short, it's pretty arbitrary. What isn't arbitrary is that some mass extinctions alter the evolutionary tree of life far more radically than others. For example, the first of the Big Five pruned away more than 80% of the species on Earth, but it left all the big branches of the tree intact. So life went on more or less as it had before. Other mass extinctions, even some smaller ones, like the one 66 million years ago, trimmed the evolutionary tree far less evenly, decimating some previously thriving branches and preparing others for world domination.
Well, Guy, I find that really helpful because it explains that not all mass extinctions are created equal, nor have an equal impact.
Yes, and as indicated in that short video, we frequently refer in contemporary language to the 5 previous mass extinctions, and so people say that we're in the 6th mass extinction, but that's a little arbitrary too, as pointed out in that short video. And I have tracked down at least 8 predecessors, and we're now in at least the 9th mass extinction event. And you can go to guymcpherson.com, use the search box, and just type in there at least the 9th, at least the 8th, at least the 7th, and so on, and find the peer-reviewed evidence for these previous mass extinction events.
So that video was great. And in fact, this is the data from Sapkowski. This is one of many charts of the data that was referred to in the video. And he cataloged all the life forms that scientists had found, and identified these extinctions. And so this is a different chart. What this shows is, if you look at the left axis, this shows the number of marine genera. And I remember from biology that there's genus and species is the most detailed character of a life form, and then genera is slightly more generic, and then family. Am I right? It's family, genus,
yes,
species.
that's correct. So for example, we are Homo sapiens, and a close relative of ours was called Homo neanderthalensis. That's what we call the Neanderthals, but it was in the same genus as us. So it's very closely related.
Right. What I like about this chart is this is a growth chart. There's 2 ways to represent this, and this one represents the growth and expansion of the number of genera, but then also the precipitous drops in it. And so these same 5 prior mass extinctions, that when people talk about the 5 extinctions and we could be in the 6th, this is what they're referring to. And what it strikes me here is the reason these are mass extinctions, Guy, if I'm right, is they're sudden and dramatic drop-offs in the number of marine genera that he found. And when it's that sudden and that dramatic, then it's a mass extinction. But as I think I've learned, there's extinction happening all the time. Is that correct?
Yes, absolutely. Extinction is an ongoing event every day, all the time. Currently, as a result of human actions, we are driving more species to extinction than has ever been documented, even in the fossil record. But at the same time, extinction is a natural event. As Carl Sagan pointed out, extinction is the rule, survival is the exception.
And mass extinctions can have many causes. We do not have time to go in to even just the scientific theories and consensus on these 5, on what has caused these 5. We can mention that the most recent mass extinction that science thinks it knows of is 65 million years ago, and that was indeed what we now think of as an asteroid impacting the Earth. But the previous ones were almost as massive and did not involve, to our knowledge today, something like an asteroid, an extraplanetary body hitting us. They happen because of what? The internal changes of the planet.
Right. And in none of the previous cases do we see any evidence of a single organism causing profound changes. These are events that happened to life on Earth. Contrast that with what we're doing today. Human actions are causing all kinds of other species to go extinct. It's not an asteroid striking the Yucatan Peninsula.
But it may have the same or worse effect of an asteroid. Our human impact in the last 200 years may have the effect on scale with an asteroid impact.
We are the asteroid and we are the Yucatan Peninsula.
Let's go to the next slide for another view. I want people to realize scientific data can be presented in a number of ways. There's always useful things that come out of a chart. This is, in essence, the reverse, the rate of extinction. And so you see the very large bumps. The named extinctions here, the 5, they're the exact same as the previous chart. It doesn't mean that one chart is correct and one chart is not. There is so many ways to present data that are trying to be helpful. But what's interesting about this is this shows it as the rate of extinction rather than the rate of growth of new species and genera and families.
And notice the extinction rate here is in families per million years. So we're not talking about species now. We're talking about a much broader category of organisms.
Right. And what I like about this chart is that it does break down the estimated loss of species, genus, and families. And you can see dramatic differences. For example, the tallest spike here on the left, the Endordovikian, from what scientists can measure, was 86% of species, 27% of genera, and 27% of families went extinct. But the next highest, and the highest one of species destruction, is the End-Permian, according to this. 96% of species, 56% of genera, and 57% of families went extinct. So a much larger extinction, even though for whatever reason the spike is not as tall, it's probably on a percentage basis there was much more life at that time, but much more of it went extinct. It's very interesting to see the scope of this End-Permian extinction. Am I right? That's regarded as one of the most major extinctions that we have.
Yes, it's sometimes called the Great Dying.
The Great Dying, right?
Because it was a big deal. And then you fast forward to the one that took out the dinosaurs and many other species.
Right.
And that was only 76% of the species that went extinct. And that's because of an asteroid striking the Yucatan Peninsula. Can you even imagine?
Right. And the asteroid, and it was not as the asteroid one by this chart did not result in quite the same level of species, family, and genus destruction as the End-Permian Great Dying.
That's right.
But it seems to have happened more quickly, so that the width of the pyramid there, it's very sharp, was quite sudden, whereas the previous ones are wider, if you will. They happened over a little bit more time in millions of years.
And that's really critical to understand. In Cretaceous, the asteroid striking the Yucatan Peninsula, that event occurred very, very rapidly. As you can see, it's a tremendous spike, and yet it played out over more than 70,000 years. The one that we're in now is playing out over about a human lifetime.
Right. And you can see that the trend is certainly upwards right now, and it will only be with hindsight of whether we're around to measure it, of what our impact really is.
Right.
This again is developed from Barnowski, who was looking at a much larger data set than even Sapkowski. So these are different scientists, all of whom are looking at this information. Some of them are putting different emphases on it, but this is just one, again, condensation of a ton of data. Let's look at the next slide, see what that shows. So this one is our last slide. This just, again, puts the graph, I like it because it puts the graph in with some descriptions. And again, the percentages are there. They're horizontal, they're sideways. The Ordovician, 86% loss. That's just characterizing the total loss of species. 75% in the late Devonian. And I think it's too small to read, but this slide, which is available from education.nationalgeographic.org, gives a brief description of what is said to have caused each of these mass extinctions. And notice that this one doesn't just name 5 extinctions, it includes a thing called the Holocene extinction. Why don't we close by reading that and see what that says. 11,700 years ago to the present. This is National Geographic.
And it says the next mass extinction may already be happening. Now that's interesting because there is little doubt at this point that it actually is happening. So I'm not sure when National Geographic produced this, but we now know better. The current extinction rate is at least 1,000 times greater than the normal extinction rate. A normal or background extinction rate is the average rate of extinction based on the longevity of species through time without human influence, determined by the fossil record. Scientists believe that human impact on the environment is the leading cause of extinctions today. And again, I don't think there's any question about that. In fact, the Intergovernmental Panel on Climate Change, in their October 8th, 2018 report, Global Warming of 1.5 degrees, says these global level rates of human-driven change far exceed the rates of change driven by geophysical or biosphere forces that have altered the Earth system trajectory in the past. Even abrupt geophysical events do not approach current rates of human-driven change, end quote. And they, of course, rely upon peer-reviewed evidence to make such a statement. But what they're pointing out is that even the abrupt geophysical events that happened in the past don't even come close to what the collective humanity is doing right now.
The chart, I would say the chart, to be accurate, what's missing in my view, and based on what even National Geographic is acknowledging here, is there should be a sharply down, the beginnings of a sharply down line there. They must not be able to represent it, obviously, in the geological time. But just as there's a sharply down line at the Cretaceous and the Permian and the other, we are already down a slope where there's more species destruction than creation. And I think that's been measured just in the last 200 years.
Oh, yes, absolutely. So there's a tremendous amount of loss that is already occurring. And they show, for example, 80% loss here during the Triassic-Jurassic extinction, 75% loss in late Devonian extinction, but they don't show the loss that's happening already with the current extinction event.
I'm reminded of the fact that the Australian continent, as recently as I think 200,000 years ago, had many dozens of megafauna species, much larger than the largest animal in Australia now, which I think is a kangaroo, or unless you count wild horses that are now there. There were giant megafauna, very large mammals and marsupial animals, from what I understand, at the same time as there were the indigenous human ancestors of today's Australian indigenous people. And that we think that even before modern industry, merely hunting and using fire hunting, which unfortunately is a method of hunting where you set fire to a whole section of forest just to drive out some animals and then take some of them down. Fire hunting was done not just in what is now Australian continent, but in many other places. Bull jumping, where you herd animals and force them over a cliff. These are very destructive methods of human conduct, needlessly, we would judge today. But they resulted. Am I right? It is a scientific hypothesis that just 300,000 or 400,000 people in Australia brought about the extinction of megafauna through their impacts.
Oh, yes. And almost certainly the same thing happened in North America.
And this is before anything called settled cities or civilization or agriculture. This is nomadic peoples.
Right. And yet what we're doing today far exceeds the damage done a few or several hundred years ago.
Insect populations, I mean, this is now news of 7 or 8 years ago. Insect populations have dropped by 70 or 80%, flying insects. A lot of Americans who take holidays driving around notice that if they're our age, they might remember that when their family took them on a car ride, especially at night, the moths and bugs and flying insects would cover the front of the vehicle and would have to be washed off in the subsequent days. That doesn't happen as much.
Right. I remember taking road trips, and my dad almost always drove, and we would stop to get gas. My dad would fill the car up with gas while my mom would take the squeegee and clean off the headlights.
Right.
They were so covered with insects that they were dimming the headlights.
Yes.
You don't see that today.
And that's a major, I mean, just in terms of statistical, an 8-inch headlight is a collection device that was being driven around at night. And if one had scientifically measured as a collection device, the impact of insects on it in the 1960s or 70s, there would be far greater numbers of insects in that collecting device than you would get today on an 8-inch headlight. So,
absolutely. I didn't know why my folks weren't collecting the data on this.
Yes, count the insects, Mom. I want to be a conservation biologist. Let's count the insects and keep a record. This session, we have gone back to everything that science knows. Not everything. We've covered it, sort of Reader's Digest level, back to the origin of the planet, and taken a look at the rise of life on the planet from very simple single-celled, single-stranded organisms into greater complexity. We've seen that it really only is in the last, if the life of the planet is a 24-hour day, it's really in the last hour and a half or so that life has arisen, anything we would call life, hour and a half to 2 hours of that day. And it's the last second or so of the day that anything related to the human ancestral genus and species has arisen. But we are having an impact on this planet through our activities that is on a much grander scale than any prior species. And we'll be talking about that in future sessions.
Yes.
Any last words, Guy, on all of what?
Yes, all this reminds me of the phrase I heard most frequently from politicians throughout my entire life with respect to this country. We're number one.
We are number one at so many things.
Absolutely. Including apparently causing the extinction of other species. And therefore, ultimately, our own species.
I have one of my gallows humor phrases, which is, I wheel it out every once in a while, which is everything is going according to plan. And that's unfortunate. Truth is a beautiful thing. And when you can get at a deeper understanding of the real case, as I call it, it at least it makes me feel less vulnerable and less crazy in viewing what is happening today, if I can understand it. And I'm hoping that for your audience, these discussions are helpful.
Yes, I mean, that's the point, isn't it? I mean, why are we here on this planet anyway, as individuals, if not to understand what's going on around us? I think this
With
is
these
important.
with these big ass brains, which take up so much of blood supply, why are we here?
Right. Absolutely.
If
Okay.
not to use them. All right.
Let's
Great
wrap it right
discussion.
there. I look forward to next week.